Okay, hey students, today we're going to look at section 5.4. So let me write a few notes about this. This is called orthogonal diagonalization of symmetric matrices. Okay, so there are a lot of words there, so let's break this down. Let's remember what orthogonal means. So that means that we have, so an orthogonal group of vectors would be a group of vectors that are all meet at 90-degree angles. Or right angles, or pi over 2, or whatever you want to say. Diagonalization, if you remember what that was, we can diagonalize a matrix. Remember, that has to do with the eigenvectors and the eigenvalues. So if you go back and remember diagonalization, so diagonalization is where we can write a matrix as, I think it's P, D, P inverse. So this is our matrix A. This is a diagonal matrix that's made up of the eigenvalues down the center and zeros everywhere else. This guy is a matrix made up of the eigenvectors in the columns. And so we can say that the matrix A is, the word we used is similar to the diagonal matrix, and the matrix that gives us that similarity representation is the matrix P, which is made up of those eigenvectors as the columns. Okay, and then we know how to find the inverse of P, finding the matrix inverse, and then that would be what the P inverse is. And then symmetric matrices, so if you remember what symmetric is, symmetric means that A is equal to A transpose. Whoops, sorry, got excited there. A is equal to A transpose. So you want a matrix that's equal to its own transpose. Well, what does that mean if I'm looking at a vector or a matrix that's equal to its own transpose? What that means is it's going to have a line of symmetry down the diagonal. So what's down here is going to be symmetric to what's up there. So I'll show you some examples of that. If I have a matrix that's equal to its own transpose, that means that if I had, for instance, A, B, C, D down the diagonal, right? And then I had E here, that would mean E would need to be over there. And if I have F here, that means, okay, I didn't really organize that very well. So if I have A, B, C, D, say this is a 4x4 matrix. So I would need to have like E, if E is here, then E is here. If let's see, where am I at? F is here, that means F is here. If G is here, that means G is here, and so on. So you'll end up with this line of symmetry, a reflectional symmetry, where these guys match up, across that line of symmetry. And so that's why this matrix that's equal to its own transpose is called symmetric. So we'll see that symmetry. In other words, if I fold along that diagonal, those guys will match up. So what we're going to learn in this section is that if you have a symmetric matrix, then it is diagonalizable with real eigenvalues. So we learned before when we were learning about eigenvalues that not every matrix is going to have eigenvalues and eigenvectors. And sometimes if the matrix is representing like a rotation or something, the eigenvalues might be complex numbers. We didn't do a lot with that, but we do know that that is something that can happen. But what we're gonna have in this section is really interesting because it puts together so many things from the whole semester. That if we have a matrix that is symmetric, then the spectral theorem is going to tell us that it's going to have real eigenvalues, it's going to have eigenvectors, and the cool thing is going to be that those eigenvectors are actually an orthogonal set. So not only do we get real eigenvalues, but we're going to get eigenvectors that are orthogonal to one another. And that is going to be a property of symmetric matrices. So this is really, really cool because it brings together so many different things. So that's where we're headed in this section. So let me give a couple of definitions and we will, and then we'll do a few examples. So the first definition is, okay. A square matrix is orthogonally diagonalizable if there exists an orthogonal matrix Q Now, what do we mean by an orthogonal matrix? I mean, we talked about vectors being orthogonal, but for an orthogonal matrix, that means the columns vectors are orthogonal. So if the column vectors in that matrix are orthogonal, then that means that the matrix is orthogonal. In a diagonal matrix D, such that Q transpose AQ is equal to D. Okay, so that's the definition of orthogonally diagonalizable. So we go back to the idea of diagonalizable, and not only is it diagonalizable, but those vectors that we get for our eigenvectors are actually orthogonal to one another. Okay, let's do a quick example. So we want to diagonalize the matrix. One, two, 2, minus 2. Okay, spoiler alert, check it out. This matrix is symmetric. So we know from the spectral theorem that we're going to get in a little bit that this guy is not only going to be diagonalizable, but it's going to be orthogonally diagonalizable. So we can kind of expect that that's what's going to happen. But let's check it out. Let's see. So how do we do this? So remember, we're going to need to find those eigenvalues first. So we want to take the determinant of this guy with, we're going to subtract lambda off of that diagonal. So we'll have 1 minus lambda, 2, 2, negative 2 minus lambda. Okay, so if I take that determinant, I'll get 1 minus lambda, negative 2 minus lambda, and then minus 4. So 2 times 2 is 4. And so that's going to give me lambda squared minus lambda plus 2 lambda, so plus lambda, and then minus 2 minus 4, so minus 6. And so that factors into lambda minus 2, lambda plus 3. So I get lambda equals 2 and minus 3 as my eigenvalues. Okay, and now I want to find the eigenvector that corresponds with those. So let's start with lambda equals minus 3. And so that's going to give me, if I do minus 3, 1 minus negative 3 is 4, 2, 2, and then negative 2 plus 3 is 1. So I want to find the null space of that guy. And so I can divide that first one by 2 and then subtract it from the second one, and I'll get 2, 1, 0, 0, 0, 0. Okay, so for the null space of this guy, here is my pivot, and so that means that this guy is going to be my free variable, and so I can say 2x1 plus t equals 0, so x1 is equal to negative t over 2, and x2 is equal to t. And so my vector that I get is going to be negative 1/2, 1, or I can, if I want to scale that to get rid of the fraction, I could use negative 1, 2. Okay. And then, so I could say that E minus 3 is equal to the span of negative 1, 2. Or I could do 1, negative 2, whatever. Okay. And so if lambda equals 2, what do I get? So 1 minus 2 is -1, 2, 2, 2 minus 2.
This is the best one.
Yeah, it's good. Okay, so that's -4, and then
question.
0, 0.
Did you
Okay,
see
hold
the-
up. Whoa, whoa, whoa. All right, so then that row reduces down to 1 minus 2, 0, 0, 0, 0, 0. Okay, and then again, so my pivot is there, and this is my t, and then I get x1 minus 2t equals 0, and x2 equal t. So we'll get the vector 2, 1 as our other eigenvector. So E2 is equal to the span of 2, 1. Okay, and so now I can say that if I let P equal the vector, so let's do -1, 2, 2, 1. And then my D will be, okay, so since the -1, 2, since this eigenvector goes with the -3, I'm going to put -3 in that first spot. 0, 0, 2. So I just have to make sure they correspond. And then, you know, this guy goes with the 2, and this guy goes with the 3. So, so there's my P and there's my D. And so what I can see there is that the V1 and V2 are orthogonal. So let's test that. So if I took my 1, 2, or -1, 2, and I dot it with 2, 1, I get -2 plus 2, which is 0. So I can see that this vector and that vector are orthogonal to one another. And I can actually make them into unit vectors if I want to. So if I took my vector -1, 2, and I multiply it by 1 over the square root of 1 squared plus 2 squared, I'm going to get -1 over square root of 5 and 2 over square root of 5. And so now it is a unit vector. And then I could do the same thing to the vector 2, 1, and I get 1 over square root of 2 squared plus 1 squared. And so I'll get 2 over root 5 and 1 over root 5. And now I have a set of vectors that are normal vectors and orthogonal. So it is an orthonormal set. So orthogonal, I said this orthogonal matrix column vectors are, and I should have put this, not just orthogonal, but orthonormal. So let me emphasize that. So not just orthogonal, but orthonormal. Meaning that they are not only meet at right angles, but they're also unit vectors. So I could let my matrix Q be this orthonormal version of this. So -1 over square root of 5, 2 over root 5, 2 over root 5, 1 over root 5. So there is my orthonormal vector. And then I'll have that Q inverse. AQ is equal to that diagonal matrix D. And so I've shown that A is not only diagonalizable, but it is orthogonally diagonalizable based on that definition. And in my musings that I was talking about at the beginning, that is not a surprise because I was telling you that we're about to have a theorem, which is called the spectral theorem. It's the big theorem of this section. And when we get to it, it's going to tell us that a symmetric matrix is orthogonally diagonalizable, and a matrix that's orthogonally diagonalizable is also a symmetric matrix. So that's a if and only if statement there. Okay, I think I'm going to stop here and upload and then do some more in a bit.